Good afternoon, everyone, here in beautiful Urbana, Illinois, and wherever you might be abroad. Welcome to the TCIPG Friday seminar, which first of every month. This is the first one for the fall semester, coming on September the 5th. And before I begin with our speaker, I would like to remind everyone that TCIPG has its industrial workshop on November 12 and 13. If you are an industry person or someone that is interested in attending, there is information on invitations at info@tcipg.org. And you're welcome to request an invitation by contacting that address. We are an organization that deals with resiliency and security with a focus on the power grid. And so we like a nice balance of seminars throughout the year. And our speaker today is Milind Tambe, the Helen Emmett Jones Professor of Engineering at the University of Southern California. And he is a very special person, a computer science grad from Carnegie Mellon, but I understand by talking around that he was also a classmate and maybe even a dorm mate of our Nitin Vaidya on our faculty here in computer engineering. So without wasting any more of his time, he's going to talk about security games. And Milind Tambe from USC, California.
Okay, well, thank you very much for inviting me, and thank you for coming to this presentation. I'm really delighted and honored to be back here again. So my talk today about science of security games is joint work with a large number of people, current and former PhD students and postdocs, as well as other collaborators from around the world. Given the large number of collaborators, I'll highlight the role of the lead students and postdocs in key parts of the presentation. So given that we have limited time, let me just jump right into the topic. Security is a global concern. We have to protect our ports, airports, critical national infrastructure, interdict the illegal flow of drugs, weapons, and money, protect forest, fish, and wildlife. In all of these cases, we have limited security resources and a large number of targets to protect, and a watchful adversary who can monitor our defenses. So how do you plan, schedule, allocate your limited resources? We appeal to game theory, in particular this notion of Stackelberg games. Some of you may be very familiar with this notion, but for the benefit of those who may not be, I'm going to use this simple 2x2 example of a defender, the Coast Guard, trying to protect the toy port. The port has two targets, targets 1 and 2. Target 1 happens to be more important than target 2. If as a result, the Coast Guard were always going to protect target 1, an adversary conducting surveillance will attack target 2. The adversary gets a positive reward of 1. The Coast Guard get a negative reward, -1. If as a result, the Coast Guard were to switch and say we'll always protect target 2, an adversary conducting surveillance will switch as well. And now the adversary will attack target 1. The adversary again gets a positive reward of 5. The Coast Guard again get a negative reward, -5. So any deterministic strategy an adversary can defeat. If the Coast Guard were to use a mixed strategy, a randomized strategy, 60% of the time they're at target 1, 40% of the time they're at target 2. An adversary conducting surveillance will only know, oh, the Coast Guard are there 60%, at target 2 40%, but what they will do tomorrow remains unpredictable. The goal here is only to increase the cost and uncertainty to the attackers. We're not trying to get at 100% security because there is no such thing. We are trying to optimize our limited security resources. Now, these kinds of games are called Stackelberg games because the security forces, the defenders, commit first to a mixed strategy. The adversary conducts surveillance and then responds. It's a two-stage game. But the defender needs to optimize the initial allocation, the initial commitment, taking into account the adversary's response. And so the question then becomes, what's the optimal commitment? Now, we said 60-40 here, but 60-40 may not be optimal. Maybe it's 70% of the time you should be at target 1 and 30% of the time you should be at target 2. For a 2x2 game, of course, we can solve this by hand. When there are trillions of possible defender strategies and large numbers of targets to attack potentially, this problem becomes difficult, and that's where computational techniques come in. So our contributions have been in terms of computational game theory in solving massive scale games, but whereas we assist the defenders by providing them decision aids, on the other side we have a human adversary, and therefore we have to exploit human behavior models. This combination of computational and behavioral game theory is a part of the key contribution of our work. When combined with AI techniques of planning under uncertainty and learning, this leads to decision aids that can be used by security agencies in the field, and therefore computational game theory in the field. With me, my students, postdocs, and other collaborators embedded with the security agencies that allows us to get data back from the field. So these are our research contributions, but when it comes to applications, we've been very fortunate that a number of our algorithms are now in use, deployed for a number of years. So with the US Coast Guard, we've deployed our algorithms for patrolling ports. This is software that's deployed in ports such as Boston, New York, Los Angeles, Houston, and others to give guidance on patrolling strategies. If you have been on the Staten Island ferry, the patrols around that, that's our algorithm for guiding the Coast Guard patrols. In addition, for the TSA, we've built software to assign air marshals to flights in a randomized basis, as well as for airport police for setting up checkpoints, patrolling the terminals, and so on. More recently, our attention has turned to suppressing urban crime in transportation system. And so here we've worked with the LA Sheriff's Department to try to suppress crime on trains, reduce fare evasion. We've also been working with the Singapore police to reduce traffic violations in that city. And the most recent of our work has been in trying to suppress crimes against the environment. And this includes trying to suppress illegal fishing, for example, in the Gulf of Mexico with the US Coast Guard, and work that's gone on with the WWF and other agencies to try to protect animals. And so this is against poachers, and this is in foreign countries like Uganda, for example. So in the rest of the presentation, I'm going to give you an overview of our research and the applications. But as I do, I would like you to take away three main points from the presentation. First, I wanted to say that all of the applications above the red line are ones that are deployed, in use, out of our lab, in the hands of the agencies for several years. Anything below the red line, that's under development, under testing, hopefully will be deployed in the future. So as I said, there are three main points I would like you to take away from this presentation. First, decision aids based on computational game theory are in daily use by security agencies because they help optimize limited security resources against adversaries. These applications yield fundamental research challenges that are leading to a science of security games. I'll point to two main challenges in this presentation. With respect to scale up to massive scale games, there's two main ideas that have emerged: incremental strategy generation and use of marginals that exploit the structure of the games to allow us to scale up to large games. Secondly, in handling uncertainty, I'll point to three ideas: integrating Markov decision problems within security games to handle uncertainty of execution, use of robust optimization to protect against worst cases of uncertainty, and use of a quantum response model to deal with behavioral uncertainty of human adversaries. The third point I would like you to take away is that current applications, such as security of wildlife, are interdisciplinary challenges. These are really global challenges that require us to merge techniques in planning, learning, as well as security games. And these are important challenges that all of computer science or other disciplines can definitely contribute to and make a difference. So with these three goals in mind, let me now provide you an outline for the rest of this presentation. I'll start from our work in 2007, which was focused on protecting airports, going all the way to more recent work on trying to suppress crimes against the environment. As I do go through these applications, of course, I'll highlight some of our research contributions. Now, you may notice that the word research challenges is in red, bold, underlined. I've done everything I can to try to communicate that we haven't completed this work. There's a whole lot more PhD theses that need to be written, but we've advanced the state of the art. I'll start by first looking at scale up and then look at uncertainty. I'll provide two kinds of evaluations. First, the standard kind of evaluation that you may see in an AI conference, which is does the algorithm really scale up when it's supposed to? Does it handle uncertainty? But the second kind of evaluation is that since we are fortunate enough that some of our work is actually deployed and in use, how does it really perform in the real world? And here I ask for your patience because this will only be covered towards the end of my presentation. And if I could get a 10-minute signal, then I'll make sure that I switch over to that at the end of my talk. So all of the work that I'm going to talk about has been published in dozens of publications in main AI conferences, AAAI, ICHCAI, and AMAS since 2007. There's also this book, Security and Game Theory, that collects a few of these papers and commentary from domain experts. And my agreement with my students and postdocs and contributors to this book is that if a lot of copies of the book sell, then from the royalties, we'll go out on a nice dinner cruise in Marina del Rey. And if not many copies sell, then it'll be a simple meal at our home. So you know what to do. So let's start with airport security, which is the first set of applications that I wanted to talk about. We started our work with Armor at LAX in 2007. We've also built guards for the TSA. I'll focus on Armor because it's the first system we built. It's also the simplest, and it's still in use. So the assistant chief for airport police at the time, Errol Southers, wanted to improve security external to the airport. And the reason was, of course, there had been 6 plots against LAX, 3 successful, 3 failed. This is serious stuff with guns and bombs. And there's, of course, this attack on the Glasgow airport in June of 2007. So I'm going to show you a small video and talk over that. There's 18 bound roads into LAX, but not enough officers to have checkpoints on all roads at all times. There's 8 terminals, but not enough dogs to be at all terminals at all times. So where and when do you set up checkpoints? Where and when do you canine patrols? We solved the problem using Stackelberg games. Sometimes that leads to arrests of people carrying large numbers of weapons into the airport. But of course, I'll provide a more detailed evaluation a little bit later on. So this is how Armor works. You start with a game matrix. I'm just showing you a 2x2 game matrix, but you take the entire game matrix. You feed it into a mixed integer program. The mixed integer program provides a mixed strategy, a probability distribution over the different strategies for the defender. For example, here it's saying the probability of having a canine patrol at 8 a.m. at terminals 2, 5, and 6 is 0.17. Canine patrol at terminals 3, 5, and 7 is 0.33, and so on. And then we sample from this distribution to actually generate a patrol. So for example, a deployment strategy. Here, for example, it's saying at 8 a.m., send the canine teams to terminals 2, 5, and 6. At 9 a.m., to terminals 3, 4, and 8, and so forth. So this is an actual schedule that we hand over to police officers. So now let's look at how the mixed integer program works. In its simplest form, we start with the game matrix as the input, and that gives us Rij. So we're trying to maximize the defender expected utility. Rij refers to the reward to the defender if the defender takes a strategy I and the adversary takes a strategy J. Xi is the probability with which a particular strategy is executed. So for example, X1 might be the probability there's a dog on terminal 1 and a dog on terminal 2. X2 might be the probability there's a dog on terminal 2 and a dog on terminal 3. Qj is the adversary's response. Now we want this to be a best response, meaning the adversary conducts surveillance of our randomized strategy, and then he may attack a particular terminal. So there are best response conditions. I won't have time to go into that. But essentially with this, Armor can start to work. The one issue here is where did we get the values of Rij, which are the inputs to this program. So at LAX, the challenge that was considered was somebody attacking a single terminal, for example, by driving in a truck bomb. And therefore, payoffs relate to the numbers of lives lost at different terminals. Now, someone has gone out, and some researcher, and figured out how many people are there at different points of the day at different terminals at the airport. And that essentially is the data that we use in our payoff matrix. Later on, I'm going to talk to you about an application we've developed for the Coast Guard. Now there, someone has gone out, a team of researchers, for every major port in the country, for every major target in the port, for different methods of attack, how many lives would be lost and what would be the economic consequences. Multiplying lives lost with a dollar figure, they get a total value for each target. And so this is hard work that somebody has done compiling all of this data that exists in databases and so forth. So we're just reading off of that to get our payoff matrix. Of course, we understand that these values are not perfect, so we have to deal with the fact that there is payoff uncertainty, and I'll come to that a little bit later on in the talk. But with all of this in work, Armor was operational at LAX in 2007. By 2008, given the advances Errol had made for security at LAX, he was in front of a congressional subcommittee talking about the enhancements he had made, and we were fortunate enough that he mentioned our work there.
LAX is safer today than it was 18 months ago. A team of research led by Dr. Milind Tambe worked with our department to develop Armor. This software randomizes our vehicle checkpoints along airport access roads and the deployment of our explosives detection canine teams throughout the airport. In the ensuing media coverage was Newsweek talking about Armor throwing a digital cloak of invisibility, which meant my colleagues at the AMAS conference next year kept asking me how was the cloaking device coming along at USC. But this did get the attention of the Federal Air Marshal Service. Their challenge is assigning air marshals to flights. We're looking at the international sector with 1,000 flights a day. And from 8 terminals and 100 actions, now we had 1,000 flights a day, complex tours, and the action space was easily 10 to the power 41. Why is it 10 to the power 41? If you just think about 1,000 flights and 20 air marshals, that's 10 to the power 41 different combinations. You should just take the program and feed it into Armor, it quietly dies running out of memory. So we needed a different approach. The basic idea is to not enumerate all the possible combinations. And here comes the first technique for scaling up, and that is incremental strategy generation, which is part of the branch and price approach from operations research. So let me give you a quick overview of how this works. This is a game in the normal form where we have along the rows the different defender strategies. We have air marshals on flights 1, 2, 3, 1, 2, 4, 1, 3, 5. So we have enumerated all the 10 to the power 41 different combinations. Along the columns are all the possible attacks an adversary could conduct. And because we have a probability variable for each possible defender strategy, now there's 10 to the power 41 different variables, and this program cannot run. So it cannot run, but if we could make it run, what we would find is that most of these xi variables are 0. In fact, we can prove that the support set size is small and only a few of the solutions exist where only a few of these strategies will have a non-zero support. So if we could just magically eliminate all the rows that would have a 0 probability, then we would get a far smaller game matrix which we could solve. And this is the idea that we exploit by starting with a very small game matrix. And then we do incremental strategy generation, so exploiting using a master-slave decomposition where the slave using LP duality theory gives us the next best pure strategy to add that is likely to have a non-zero support. And we iterate in this fashion until we converge to a global optimal. But the global optimal now may have only 500 strategies rather than the 10 to the power 41 because we've concentrated only on strategies that were likely to have a non-zero support. So this is how we make IRIS work. This is the program that's been in use by the Federal Air Marshal Service since 2009. If you've been on an international flight by a US air carrier, whether there was an air marshal on your flight or not may have been determined by this program. It led to a significant change in operations of the FAMs. In 2012, we were fortunate enough that our work was again mentioned in a congressional subcommittee hearing with the acting head of FAMs saying that in 2011, the Military Operations Research Society selected a USC project with FAMs on randomizing flight schedules for the prestigious RIST award. So these are 2 deployed applications, and by 2009 we had deployed these 2, but there were other world events taking place at the time. Some of you may remember in 2008 was an attack on the city of Mumbai, and that's the Taj Hotel on fire. I grew up in the city of Mumbai, actually just 2 or 3 blocks away from that hotel. On one of my trips to Mumbai, I saw checkpoints being set up. So after coming back to USC, I thought about casting the problem as a game on a network. So this is just the southern tip of Mumbai.
The two red pins are possible terrorist targets, two blue pins are possible terrorist sources. There's 150 edges in this graph, and if you have two checkpoints, that's 150 choose two different defender strategies. If you think now also about different attacker paths from the sources to destinations, the game becomes really massive to solve. But again, we can use this incremental strategy generation, this double oracle approach. You start with a small game matrix. A defender oracle gives a defender best response. Attacker oracle adds an attacker best response. And we iterate in this fashion, again, converging to a global optimal. And the reason we converge to a global optimal, even in this case, is because the support set size is small. Even though there's 150 different edges in the graph, the checkpoints only get set up on 6 of these roads, with the thickness of the red line showing the probability with which the checkpoint gets set up. And so by exploiting this small support size, we can solve massive scale problems. So in fact, for the entire city of Mumbai with 20,000 roads, 15 checkpoints, we can solve this in under 20 minutes. So excited by these results, I went to the Mumbai police headquarters. Now I'd only seen the inside of the police headquarters in Bollywood movies. So walking up the stairs of the police station with armed Mumbai policemen saluting me, I had the sense that I was part of a Bollywood movie. But inside, there was no song and dance in honor of Nash or Stackelberg, but it was the commissioner and senior officers wondering if game theory would do the job or not. And so this remains to be seen. So these ideas of incremental strategy generation could also be used in social networks, for example, towards counterinsurgency or for cyber networks. So now I have outlined for you one particular approach to scale up, which is incremental strategy generation. Now I'm going to talk about a second method, which is use of marginals. And here I'll turn to the ports. The ports of the United States are responsible for large fractions of the US economy, but there are threats to the port. A raid on the Bin Laden compound in May of 2011 yielded documents talking about attacking oil tankers. The Coast Guard are ultimately responsible for protecting the ports. To assist the Coast Guard, we built a system called Protect. So Protect is an acronym, so you'll see we've spent enormous amounts of time trying to come up with good acronyms. This system was first deployed in 2011 in the port of Boston. The Coast Guard tested it, and by 2012 considered it a success. And I'll come to some metrics of that they used a little bit later on. They made a short video for us. I'm going to clip it down because of constraints of time. But here's what they said after the first deployment of Protect.
The result was invigorated boat crews, more focused upon providing effective presence, reducing predictability, and enhancing the safety and security within our ports. Protect guided patrols became a source of pride for Station Boston crews, and it doesn't get much better than that. Protect has also had other positive side effects, such as the development of better tactics, techniques, and procedures. The results have been exceptional, and we continue to refine the products for what I hope will be an eventual service-wide use.
And this hope is now turning to reality with Protect in use in New York, Houston, Los Angeles, and going to other ports in the country. Whereas generating patrol strategies in ports is one part of Protect, the other part is generating patrols around port traffic, such as with ferries. Some of you may have been on the Staten Island ferry that runs between Manhattan and Staten Island. Here's a small video. 60,000 passengers a day. It's considered a big terrorist target for somebody to ram a boat into the ferry. The Coast Guard run these patrols around the ferry. These are our algorithms at work. This is a radical shift from how the Coast Guard used to do these patrols before we started deploying these game theoretic algorithms. And this is solving the game in continuous time. But I'm going to now talk to you about how to solve these games using this other approach to scale up. So A, B, C are 3 possible locations for the boats. 5, 10, and 15 minutes are possible times. And so a ferry could go from C at 5 minutes to B at 10 minutes to at 15 minutes. So that's a path a ferry could follow. Each of the boxes with the red boundary is possible point where a terrorist could attack this ferry. Now, to protect the ferry, we can run patrols. For example, the green patrol that goes from B at 5 minutes to C at 10 minutes to B at 15 minutes. Or the brown patrol or the blue patrols. A patrol can protect the ferry right next to it, and therefore we can now solve the problem exactly as we did armor, that would generate a probability distribution over each of the patrol routes, so brown patrol with a probability of 0.17, green one with a probability of 0.13, and so forth. This would work. Unfortunately, each patrol route is a variable here that's n to the power t variables, and it cannot scale up. But instead of taking these routes as variables, if we take segments of these paths as variables, so if we take the green and the brown segment together and send a single probability flow over this particular segment, and if you take the blue ones together and use a single probability flow over this particular segment, by using probability flows on individual segments rather than route by route, we can reduce the number of variables to n squared multiplied by t. And this does scale up. And now we can, from there, extract the probabilities over routes that we wanted. So if you, and this can be scaled up to continuous time games also. Now, so if you see reports on CNN like, the US Coast Guard means that I feel safe and so forth, you now know that it is a game theory at work. In 2013, we were again fortunate that the Coast Guard mentioned our work in a congressional subcommittee hearing.
We're working with the University of Southern California to utilize game theory as a way of optimizing and scheduling our patrol. Makes it harder for somebody to anticipate where the patrols will be. So even though we're having to slide back operations a bit, what we're working on is ideas that will allow scheduling that gives the appearance that we're out there a lot more than what we are.
So at this point, let me go from a scale up to handling of uncertainty. And here I'll turn to trains in Los Angeles. And now on, I'll talk about domains where there's frequent interaction with adversaries. The first domain here, we are patrolling against fare evaders. So we have our metro train system, which is a barrier-free system. People can get on and off the train without purchasing a ticket. So the Sheriff's Department conducts randomized checks against these fare evaders. To assist the Sheriff's Department, using our transition graph representation, we came up with a highly optimized, randomized schedule. So we tell we give them a schedule that says 9:13, get off at this station, start checking people. 9:23, get on the next train, start checking people. And we give this schedule to them and expect that they'll start executing it. Except at 9:22, the officer says, I have to take a bathroom break. Now we can't say, well, there are no bathroom breaks in a Stackelberg equilibrium. We have to respect that. And in more important interruptions are the fact that there are arrests that these officers may make. And so all of this means that there is a defender execution uncertainty. What it means is that we want to send a probability flow of 0.30 from B to C, but there's a 0.05 chance here that the officer remains at station B. So we can use MDPs integrated into security games to handle these kinds of uncertainties. Now what we get are policies that can be loaded onto smartphones. And so even if there is an interruption, there's always an action available to take next for the officer. The same idea of MDPs is in use in other systems we are developing against opportunistic crime, for the street system with the Singapore police against reckless driving, and more recent work focused on distributed Markov decision problems that brings together early work on teamwork under uncertainty in the context of security games. So here we have two officers or more who are underground, who can't quite communicate with each other but must coordinate and under uncertainty, and DEC-MDPs provide us that framework. But execution uncertainty is only one kind of uncertainty that we need to deal with. Other uncertainties exist as well. Payoffs may not be precise. All we have may be an interval over payoffs, not point estimates. We may not be certain about how much surveillance is really going on. We may not be certain about the adversary's level of rationality. Our early work, different theses that focused on individual uncertainties and algorithms that focus on individual uncertainties. More recent work has tried to combine within a single framework handling of all of these uncertainties and shown that this is a better approach than trying to optimize against individual uncertainties, no matter how much we tweak them, how much we tune their parameters. Let me now turn to the final set of applications and the final kind of uncertainty that I wanted to talk about, and that's bounded rationality. So this application includes working to protect forests, and this is some early work that we did. Following that is more recent work that is with the US Coast Guard, trying to protect against illegal fishing in the Gulf of Mexico. The challenge here is fishermen coming in from across the border into US EEZ to take away fish. To protect against that, the Coast Guard conducts patrols. We generate patrol patterns for these kinds of planes in the Gulf of Mexico, and that allows them to spot illegal fishermen. More recent work, though, and the same technique is used in this more recent work, which is against poachers for protecting wildlife. This is work done in collaboration with NGOs like WWF and WCS and so forth. Some of the work has gone on here with our colleagues in the Queen Elizabeth National Park in Uganda. What you see there are pictures of rangers, and we're trying to improve the patrolling strategies of the rangers. What we are fighting against are poachers. These poachers lay down snares, such as the ones shown here. The idea here is to trap the animals, and what it does to the animals is too brutal to show here, but you can Google it if you wish. So it does also, though, give us data on how the poachers are acting by locating where the snares are. And that gives us a model of the adversary, and then we can generate patrols against those adversaries. Now, let me take a minute to talk about poaching. All of us are familiar with poaching. It's been going on for decades. Well, what's going on now is a catastrophe for wildlife across the globe. You may or may not know, but tigers are completely wiped out from some Asian countries. The World Bank runs a program to try to save the tiger from extinction. And so we believe that computer scientists, people from other disciplines could all contribute to this important challenge. So we are going to, while getting data back from the field with these snares and so forth, now that we are deployed, our software is one way of getting data. Another way that would allow us to speed up getting of data is to run simulation games. So these are games run on Amazon Mechanical Turk. So here we have a simulation where we are showing a protected area. The green boxes are boxes where there's very little range of patrolling going on, and so the probability of capture is very low. Red are where the probability of capture is very high. We show animal density, and now people play for real money as poachers. So our algorithms are going to generate the defender strategy, and people are going to play as poachers. And they can go around and find a place to lay down a snare. If they capture an animal, they get money, they win. If they get captured, if their snare is removed, then they lose money. And so we've played large numbers of such games in different simulation environments with large numbers of human subjects. And our initial results, starting from 2009, were something like this. So this is showing you along the x-axis different observation conditions. Unobserved means we give the adversary, the humans, no observations about defender strategies. 5 observations, we give them 5 samples. 20 observations, we give them 20 samples. Unlimited means we give them exactly the probability distribution that we are playing. On the y-axis is defender expected reward. Lower is worse, higher is better. Blue is armor. This is our optimal approach, of course. And red is uniform, and what we see here is blue is better than red. So even against people who are boundedly rational, our optimal approach is better than doing something very simple like a uniform random approach. But the main point here is that there is another strategy, Cobra, which is better than optimal against people, and it does so by exploiting human biases and weaknesses. Specifically, if you tell people there's 8 targets and 1 guard, they come to the table saying, well, there's a 1/8 chance of seeing a guard at each of these targets. Now you show them samples saying it's not 1/8, it's not a uniform distribution, but they have anchored on uniform, and no matter what you do, it seems to be hard to move them away. So so they have invented phantom forces in their head, and we can exploit that to do better than optimal. Specifically, we are going to play a strategy X. The adversary is going to observe a strategy X prime, which is a linear combination of X and the uniform distribution. And then there's epsilon optimality. Anything with an epsilon of the optimal, people may consider as optimal. So with these 2 ideas, Cobra did better than armor. But the one weakness of Cobra was the fact that there's this hard bound of epsilon. So we wanted something softer, and to that end, we turned to the control response model, which is a stochastic choice model. The basic idea here is that we're not trying to maximize expected utility, or rather, we're not modeling people as just maximizing expected utility. But any target with a high expected utility, an adversary is more likely to select. A target with a lower expected utility, an adversary is less likely to select. But the likelihood is not 0. So it's sort of a soft max function. So this is how we are modeling an adversary. And that leads to a nonlinear, non-convex optimization problem. Once we get over that, what we get then is we can then run human subject experiments, modeling the human as following this quantum response model, and running many human subjects. These are 4 games that I'm showing you results for. Defender expected reward on the y-axis, higher is better, lower is worse. Quantum response shown in red significantly outperforms both Armor and Cobra. So this was the work of my student Rong Yang. James Pita's work was Armor and Cobra, and he was halfway through his PhD thesis when Rong joined our program. And for a year of research group meetings, Rong would come in and show her results showing how her work with the quantum response was outperforming James's PhD thesis. And so after a year of listening to Rong showing how her work was better, James struck back in coming up with a different approach. The basic idea is robustness. His point was we don't need to really model an adversary. All we need to do is to bound the loss to the defender. So we are going to take our Armor program and add an extra condition that adversary's utility loss bounds the loss of the defender. So the adversary deviates from optimal and gives up 10 points. The defender can give up to 10 points. If the adversary deviates and gives up 5 points, the defender can give up to 5 points. With this idea, James went to AMT, Amazon Mechanical Turk, played 100 games. And here he showed that with large numbers of human subjects with statistical significance, 42 of those games, so these are games with 8 targets and so on and so forth, of 24 targets and so on, 42 of those games, his robust approach outperformed quantum response. Quantum response could only outperform in 6. So his approach had won. Being clever enough, he said, this is it, I'm getting my PhD, and he left USC, and that was a good thing, because right afterwards, Rong came back and said, I can do better than robust. If only I changed the quantum response model to look at subjective expected utility rather than expected utility. So rather than taking the normal expected utility, we are going to take a weighted sum of probabilities, rewards, and penalties as how people may be modeling this problem. So we're going to model people as selecting targets based on this subjective expected utility. And with this idea, then, she played for 22 games and showed that in 13 of those games, SUQR, the new model, outperformed robust, and robust only outperformed in 1. So clearly, she had outperformed robust. But one criticism here is that we had to learn the weights, W1, W2, W3, from data. So the question is, how would this perform in a different population? So our colleague and collaborator, Sarit Kraus, took the weights that were learned from AMT and went to an Israeli security expert, an intelligence unit, and had them play the game using the weights that were learned from AMT, and showed that even there, SUQR did quite well, 6 against 3. Now this competition between a robust approach and modeling an adversary, this is not settled. It needs to go, this research needs to continue. Clearly, where there is data, it's possible to use an approach that would model an adversary, such as a quantum response model. And that's what we've done in the recent work on the PAWS, Protection Assistant for Wildlife Security, another acronym for you, which is a repeated Stackelberg game. So basic idea here is we're trying to build a decision aid for the rangers, and this is in Uganda, for example. So a defender would calculate the mixed strategy. So this is the randomized patrol strategy. Rangers would execute patrols. When the poachers attack targets, what we get is data of the crimes that were committed, and with that data, then we can learn the weights of our model. And we've enhanced the SUQR model to allow for heterogeneity in the poacher population. Once we have learned a better model of the adversary, we can repeat the game with a better defender strategy calculated. We simulated this area of the Queen Elizabeth National Park on the x-axis. This is a simulation. On the x-axis are different rounds of the game. On the y-axis is defender expected reward. Lower is worse, higher is better. Maximin is a non-learning algorithm. PAWS is a learning algorithm. You can see that PAWS does better than Maximin. But the lines are all trending downwards because poachers are winning. It's just that the rate at which they win is lower with the non-learning algorithm. But this is a simulation. How would it do in the real world? We were not satisfied in the simulation, so our colleague and collaborator, Andrew Lemieux, took the software and tested it out in Uganda. And so these are pictures from him doing these patrols. So this is en route to on one of the patrols. And so this is work that's ongoing. I'll be joining Andrew in the fall, in October, to continue these tests forward. And there's much to learn here, and there's company called Shadowview, which is a UAV company that we are also collaborating with to also help us in these patrols. So for us, we believe that this domain presents an important challenge, a research challenge, which is an interdisciplinary challenge for the research community to contribute to saving of wildlife. So with about 10 minutes remaining, I'm now going to switch to evaluation of this work. As I said, these systems are deployed, but evaluating these deployed systems is not easy. What I'm going to focus on here is to illustrate that game theory leads to an improvement over previous approaches in allocating limited security resources. And by previous approaches, what was there before was either human schedulers or a simple random approach like rolling of dice. And we've tried to show that using various approaches, certainly lots of evaluation in the lab, for example, with a simulated adversary or human subject adversaries along the lines of the Amazon Mechanical Turk I mentioned. But we have also done field evaluations looking at patrol quality. Were the patrols unpredictable? Did they cover the right set of targets? And here we have compared real schedules before and after our software was deployed. We've done scheduling competitions, human against game theory, trying to get them to see who does better. We've also run tests in the field trying to capture adversaries, mock attackers, as well as real adversaries. Who has a higher capture rate, game theory or a human scheduler, for example. And in all of these cases, what we've shown is that game theory's performance is superior. And the reason this happens is that previous approaches have weaknesses. If you think about human schedulers, they tend to fall into predictable patterns. I'm going to show you data from the Coast Guard. But if you think about the amount, and the humans also take a lot of effort. So for example, if you think about somebody scheduling for the FAMs, there's thousands of flights. Flights have different risks. The duty hours, off hours, complicated tours, tour constraints. After all of that is done and schedule is created, we say you got to be random. And it's hard for a human being to accomplish all of this. And software is just better at it. If you think about something simple like a dice roll, this leads to wrong weight in coverage. For example, officers may be sent to sparsely crowded terminals. In any way, a non-game theoretic approach just doesn't take adversary reaction into account. A final argument is that these are now multiple deployments over multiple years in multiple locations. There's no way for me as a professor sitting at USC to tell the Coast Guard in New York to use our software. So the fact that this is still in use tells us that the software must bring some value to these agencies. So I'm going to now show you some quick evidence in support of the claims I just made. Given the limited time, I'm just going to be able to show you some limited amount of data. I have a lot more. But this is, of course, a simple simulation. On the x-axis are schedule sizes for the Federal Air Marshal Service, the IRIS system. So we have air marshals being put on planes. We have an adversary conducting surveillance and then choosing a flight to attack. And we put the air marshals on flights in the simulation, either using a uniform approach, a weighted random approach, or IRIS. And we can see that defender expected utility shown on the y-axis is much higher with IRIS than with the other approaches. Now, this is a simulation. This is data from actual Coast Guard patrols in the port of Boston before Protect was deployed. On the x-axis are different days of the week. On the y-axis is how frequently different targets were visited. Green line, for example, at the top is one particular target. How frequently was it visited during different days of the week? And you can see two main points here. There are very few patrols on day 2, a good day to attack the port. And secondly, all these lines crisscross. It's not the case that the more important targets are visited more or less important targets are visited less. There is just a mishmash of all kinds of visits to different targets. If we go to Protect, what we see is that the more important targets are visited more frequently, less important targets are visited less frequently. On any given day where the boat will go remains unpredictable, but on average, more important targets are visited more. If we convert this into, and of course, a situation like a dip on day 2 all goes away. If you convert this into defender expected utility, there's a 350% increase in defender expected utility from before to after Protect. For the IRIS system, there was a 6-month competition between the human scheduler and IRIS. They had to schedule air marshals on flights for a 6-month period. And it was at the end of the 6-month period that IRIS won the competition. It was seen to be clearly superior to the human scheduler along different statistical metrics. And there's a GAO report, a Government Accountability Office report, if you wish to look at the weaknesses of human schedulers. So humans actually do a worse job of scheduling in these circumstances, but they also take a lot of time. At LAX, for example, there's a saving of up to an hour a day in scheduling by use of Armor. The same thing, humans taking a lot of time and producing worse schedules, was also seen in a competition that we ran, game theory against humans, scheduling 90 officers on metro trains in Los Angeles. So that's a picture from the day we ran this exercise. So humans were asked to schedule 90 officers on trains. We generated the schedules using game theory. We had neutral observers rating who did a better job. Humans took 2 days to produce the schedules, and in the end, produced worse schedules than game theory according to the people who are rating these schedules. So these are different security questions, and we can see that the security score of the game theoretic approach is higher. We've also done field tests using mock attackers. This is done by the Coast Guard, where they deployed mock attacker teams of people who act like terrorists in Boston before and after Protect, and their claim was that the deterrence had improved. There's also additional real-world indicators from Boston. For example, the boaters questioning, has the Coast Guard recently acquired more boats, when in fact the number of hours of operation had been trimmed down, but by changing of schedules, there's an appearance there were a lot more boats on the water. And post-Protect, there were actual reports of illegal activity in the port, which didn't exist before. Another test we ran is a control test. Here we had game theory, so officers on metro trains being asked to catch fare evaders. On the one hand, they were given schedules on smartphones using game theory. On the other hand, using uniform random. They, of course, didn't know which one was which. And they were just told to go catch as many fare evaders as they could. This test was run for 21 days of patrol. Conditions were kept as identical as we could. And of course, this is a real test with real officers doing their real job, so we couldn't quite force them to exactly only follow the schedule that was given to them. So we gave them the freedom. If they didn't like a schedule, they could always change it and go somewhere where they could find more fare evaders. And what we found is that anytime they were given uniform random, they didn't quite like it, and they changed it to go somewhere where they could find more fare evaders. And so what we have is game theory acting against a random plus human, a random uniform random schedule plus human intelligence. And we looked at how many fare evaders were captured. And what we see here is that per 30 minutes, if you look at 30-minute interval, the rate of capture of game theory was higher against these fare evaders. So this is a control test. There's also uncontrolled test in the sense of data just coming in. So this is before to after Armor. At LAX, the numbers of arrests has significantly gone up. Finally, this is a bit of boasting, but I hope you'll excuse it in the interest of science. So this is us, me and my team, receiving commendation from the Commandant of the Coast Guard, commendation from the City of Los Angeles, a certificate of appreciation from the FAMs, and so forth, all trying to indicate to you that the software is appreciated by these security agencies. So I'll end here with a summary. The 3 main points I wanted to make. Decision aids based on computational game theory are in daily use by security agencies. They help optimize the use of limited security resources against adversaries. These are applications that yield fundamental research challenges leading to a science of security games. And I talked about 2 main challenges, scale-up and uncertainty, and ideas such as incremental strategy generation, use of marginals, use of counter-response model, and so forth. And finally, current applications such as wildlife security are massive-scale interdisciplinary challenges where we as scientists can really contribute. So I'll end here. For us, this is just the beginning of research on security games. We are very pleased with the massive amount of follow-up from privacy audits to software testing to sports event security and many other works that have followed theory and applications. We are also, for ourselves, next step is ArmorWay, which is our startup. The first thing that happened after startup was PhD students quitting jobs, good jobs, faculty jobs, to join the startup. So that suddenly created a lot of pressure to do well, and hopefully we will start to do well soon. We're beginning to have people sign up for us to compute equilibria. So our goal is to sell 1 billion equilibria. And finally, game theory in the field. So I wanted to end by thanking our sponsors, and thank you for coming, and thank you for your attention. Thank you.
Great presentation, Milind. This is Tim Yardley from the University of Illinois. One of the things that's wonderful about the work that you've done is that it's actually gotten out into the field and you get data back. So thinking about this in terms of a cybersecurity context, where you can use game theory to reason about your attacker and predict potentially what they're going to do, and you may have data coming in as they attack you. But what about the preemptive sort of activities where you don't have that data to verify and you're trying to shore up your defenses before you get attacked? Any thoughts on that?
So I guess the way we've dealt with that, and in the early work on counterterrorism and so forth, is that essentially you are now reverting. One way that's going on is that you're reverting to a assumption that the adversary is perfectly rational because you really have no data, and so they are basically going to act in their best interest. But also that there's a lot of uncertainty. There's uncertainty about what are the payoffs, uncertainty about how much do they really know in terms of surveillance. And so then sort of running a much more robust optimization against this uncertainty. So that would be the kind of approach that we would follow in such circumstances. But we really have not pushed into cybersecurity. We were very eager to, but that's just not something that's come up yet.
Hi. With respect to the approach to the scaling, is it possible that you could have a hierarchy of strategies, and so that a strategy might be, deploy on flights to certain destinations, and then within that, particular carriers and so forth, and that this can kind of give you a drill down capability, and maybe you look at different parts of the problem at different scales?
That's a wonderful suggestion. So basically, this sorts of hierarchical abstraction approach is, of course, common in AI planning and so on. And they're used in computer poker, which is, the other big place where, in our field, game theory gets used. We haven't yet used that, but that's definitely a very interesting idea.
Okay, I'm Tom Overby from University of Illinois. Game theory is used in a lot of applications, and you've specialized in security here. How is that different than other applications of game theory, or is it pretty much the same?
Well, there's the following difference in terms of applications of computational game theory, which is what I'm focusing on here. I'm not aware, actually, of other applications of computational game theory that are in wide-scale use. And so in terms of proposals or what could be done to what is being done here, one big difference is the fact that because this is applied, this has given us some new insights, and essentially we focused ourselves more on the security games. The security games have a certain property. So there is a payoff structure that's slightly different than a general payoff structure. So it's got more of a zero-sumness type quality, which we can exploit in scaling up. And so there are some properties of these security games. It's also a Stackelberg model as opposed to a simultaneous move game model. And so because of all of these kinds of specialized properties of these kinds of games, it's sort of developing its own set of techniques. Now, obviously, it's game theory, as we know, such a long history of illustrious contributions and all kinds of interesting work. So it's obviously one part of the overall umbrella, but it's sort of developing its own specialized models and techniques, in my view.
Thanks.
Hi,
Jerry DeYoung from University of Illinois. Like the talk very much, thank you. I also like adaptivity over robustness, being in machine learning myself. And there we're assuming a space, parameterized space of possible behaviors. Now suppose the opponent reads your papers and knows this space, and he doesn't know the parameters, but he knows the space. Can we say something about how much he can hurt you?
That's really a very fascinating direction. So in the past, we were saying, well, this is a single-shot Stackelberg game. There is no learning going on. There's nothing going on. And so, it's a Stackelberg game, so the adversary we assume adversary knows our strategy already, so there's nothing that the adversary could gain by knowing our algorithms or anything like that. Now that we are getting into these repeated Stackelberg games and trying to learn adversary model parameters, there's a real danger that if a set of adversaries coordinated and said, okay, if we are going to fool these people by getting them to attack protect one area, and then we're going to send a big quantity of drugs on this side of the border or something like that. That can be a real problem for us. And this is ongoing work. This is actually very fascinating work. And we are really trying to understand what can happen and how much a learning algorithm could be fooled if, even inadvertently, even if people aren't being very, very smart in trying to deceive us, just by how things are, they may just happen to sort of fool the algorithm into over-specializing, and then we suffer. Now in computer poker, which we look to because it's the other big area of work of game theory in our literature, they have device strategies for non-exploitability by an opponent and so on. So that's one avenue for us to look at. But yeah, that's really a very fascinating area, very, very interesting area that we haven't yet conquered. And yeah, very interesting direction.
Hi, this is Grace Gao from University of Illinois as well. So I really enjoyed the talk. Thank you for that.
Thank
you.
you.
I was just wondering, have you ever thought about having multiple attackers, and even probably the multiple attackers have different strategies?
So I should say that the most general algorithms we have are agnostic as to how many attackers there are. They can work even if there are a large number of attackers, except that they can't quite scale up. So when you start to scale up, that's where we start having to make assumptions like, okay, assume a single attacker and so forth. There's another group at Duke, Vince Konitzer and his colleagues. So they have been looking very much at this problem of multiple attackers. And some fascinating, interesting things come out. The computational complexity with multiple attackers of Stackelberg games jumps from polynomial time to NP-hard, and the Nash equilibrium becomes much more easy to compute. And so it's got some very, very interesting properties, this space of multiple coordinated attackers, not if they're independent, but if they're really coordinating. And so it's a whole interesting area for us to look at. And yeah, it's, as I said, this is just the beginning of security games for us. There's a huge amount of work to be done. There's dozen groups easily who are working on this, and so we're really thrilled to see all kinds of different things coming up. That's a very interesting idea.
Thanks. I have another question, if you don't mind. So I think it's very interesting to see how you scale up your algorithms, and by eliminating the zeros in your big matrix. So I just wonder, what is the trade-off? I assume you will have to compromise some of the performance.
So it converges to a global optimal. There is no trade-off there. It's really doing this column generation. So we're borrowing from work in operations research. And so this is guaranteed optimality because we start with a small number. So what it means is that in the worst case, we may not get any improvement in scale up. So you could kind of devise game matrices where we really have to have all of them in the game matrix. What we are really exploiting is the fact that there is redundancy in the game, in the strategies. So some strategies cover kind of the same set of targets, so we don't need both of them, or we can eliminate some of them. That's what we are. So there is no trade-off here in this case.
Okay, thanks.
Thank you.
All right, I think we just have a couple of minutes, so we probably have to close it off here. Some of you have an opportunity to speak with Professor Tambe afterwards. Thank you for coming out. Fascinating talk, and it gives us much to think about. We have a different payoff structure because in cybersecurity it's very asymmetric relative to maybe what you presented. But still something to think about when you have limited resources and an intelligent adversary, and I think that's the key for many of us to take away. Next month we have we're going to have a presentation from within, and Grace, who just asked the previous question, will be one of the presenters, and it will be about some of the work that many of you have been following on the the wide area measurement timing vulnerabilities due to GPS and the various mitigation strategies that Alejandro Dominguez Garcia and Gray Scow have been coming up with. It's a subject of deep interest to our client and to many people in the field. So we all look forward to that. That will be first Friday in October. And with that, I think we thank the speaker one more time, and let's have a good weekend. Thank you.
So thank you very much for inviting me, and thank you for coming to the talk. Thank you.
Okay, and one more thing, once again, that Pete mentioned, the industry workshop, November 12 and 13. Info@tcipg.org. I'm looking at my Sherry and Amy. Yeah, that would be where you would write for more information about it and ask for an invitation. Thank you.